spaces of analytic pi-gamma module and spaces of p-adic automorphic form.
Yeah, thanks a lot for the introduction, and thanks a lot to the organizers for inviting me. It looks like it's going to be an amazing conference. So I want to talk about kind of some work which has been in progress for quite a while, trying to describe spaces of p-adic automorphic forms in terms of moduli spaces of Galois representations, or maybe rather of gamma modules. And let me start by trying to give an overview, explaining kind of where this comes from, the context, and maybe the aims of the talk. And at least for this overview, I beg you not to be too critical with me. I will kind of state statements in a rather rough form, and it's maybe easy to produce counterexamples for what I literally wrote. So at least for the overview, don't be too critical. So,
can I make a request? that board at the back is really not very legible when written on. It's kind of shiny. Could you
I
use
see.
one of the other blackboards?
Okay. I was trying to be smart. I mean,
maybe it's just my eyesight. I'm quite close, and I still am having.
I see. Okay. For the tartlets, maybe still fine. Okay, so the story starts maybe with the work of Kissin on overconvergent p-adic modular forms, and then was taken up, let's say, by Bella E. Chenevier and many others. So I won't be able to give a complete list anyway, so let me maybe stop here. Which results in something that one might call some overconvergent version of a Fontaine-Mason conjecture. And I just want to mention, kind of give you a rough formulation. Okay, so I want to fix the following things. So let G over Q be a reductive group, and let's say, for the sake of simplicity, it's just a form of GLN. So that I can produce Galois representations with values in GLN out of automorphic forms. And I maybe want that it's split at P. So this will rather be either GL2 or a definite unitary group. When I later on specialize to some precise setup and some precise formulations. And I further want to fix some tame level. Okay, and again, for this talk, I want to avoid talking about bad places away from P. So L not equal to P. So which basically means that I want to assume or pretend that KP is hyperspecial. Just in order to kind of lose, get rid of too many details and too many kind of technical things. Okay, then what should be the rough formulation of some overconvergent Fontaine-Mason conjecture is that the system of Hecker eigenvalues of H, which is kind of a Hecker algebra which has some part away from P and some part at P, which maybe it's some Archimedes ring, which acts on overconvergent finite slope forms of tame level KP. So this is a Hacker algebra away from P. Just a typical Hacker algebra, at least if we are kind of following this simplification. This is a kind of Atkin-Lehner wing of Hacker operators at P. And it acts on some space of overconvergent finite slope p-adic automorphic forms. And these systems of Hacker eigenvalues should correspond to Galois representations, which are anonymified at the good places away from P, and which have some kind of p-adic Hodge-theoretic condition at P that already occurred this morning, namely the triangle at P. So, and maybe they should be kind of odd continuous representations of the Galois group of Q into GLN, well, of L, which is maybe some finite extension of QP. Well, I've worked at G at the form of GLN, so my representations are n-dimensional, which are unramified at good places away from P, so good places with respect to my tame level, and which are triangular at P. And in case you don't know what this precisely means, I will even kind of recall what this means later. Okay, and actually, it's just a system of Hacker eigenvalues. I maybe shouldn't talk about Galois representations, but rather about pseudo characters and things like this. But it's all kind of inside the kind of range of rough formulation. And this has a kind of maybe geometric reformulation. In terms of the eigenvariety, so the geometric object which precisely parameterize these systems of Hacker eigenvalues that occur over here. So we have what maybe was called E this morning, what I just want to call Y, that is the corresponding eigenvariety, which parameterizes such eigensystems. Okay, so the points of this rigid space are precisely the eigensystems that occur over here, and hence, more or less by definition, they lie. This lies as a closed rigid subspace of some. Well, I mean, like, I now want to be a little bit vague. Kind of the, if you want the spectrum of this Hacker algebra and then some geometric object attached to this, which doesn't quite live in the correct category, so not in rigid spaces, you should rather maybe take, as David did this morning, some big Hacker algebra acting on space of all p-adic automorphic forms, and then which is maybe a semi-local ring, and then take its formal spectrum, rigid generic fiber, and so on and so on. But I just want to say that there is some space of Hacker eigenvalues away from P and some space of Hacker eigenvalues at P. So this is kind of a space of the space of Hacker eigenvalues. Okay, so that's kind of the geometric objects that you encounter on the automorphic side when you consider eigenvarieties, respectively, Hacker eigenvalues in overconvergent finite slope spaces. And hence, if you believe in this philosophy, there should be a kind of Galois theoretic way to say what the space is. And this was Kissin's idea of what he called a finite slope space. So this one here maybe should embed by, or maybe the way I'm doing this is maybe the other way around. Okay. So well, I have this some space of all possible Galois representations. So there's a space of all Galois representations which are unramified at the good places. So without putting any condition at P, and then in there you should cut out.
We arrow this way.
Well, because here I'm not like, you're right. I mean, like, it's just because the space is so like, this is just a very vague thing. So certainly there's a closed subspace of this, which comes from the actual big Hacker algebra. Here we just take all possible Hacker operators. So it's way too big to say that you can construct Galois.
Some abstract. Here it is.
Well, exactly. Okay.
Just like polynomial ring in Canterbury many values.
Exactly. And then in there you really have the space defined by the big Hacker algebra. And on that you should have a map from the subspace to this, which actually is an isomorphism. And that's why. So it's a bit counterintuitive. Okay, and then in here you have maybe X trie, so which is a Zariski closed subspace of representations which are triangular at P and which are kind of have something called parameters in T hat, in the subspace of triangular representations. And also this one I will maybe define in more, or recall in more detail later on. And then the reformulation of this overconvergent Fontaine-Mason conjecture would say that this is just the same space. Okay, so that you have a well, Galois theoretic way to describe what your eigenvariety actually is. Okay. So that's in some sense, at least when it comes to conjectures, an older story, which maybe in the GL2 case already was present in Kissin's paper from the early 2000s, I think. So what is the upgrade I want to propose, or what's the aim of this talk? So first of all, one of the aims is that I want to recall for you what this Galois theoretic guy here actually is. It's not new. But what is new is what I always consider to be slightly unsatisfactory about this very nice picture is that it doesn't tell you really what the space is. It only tells you what the kind of Hacker eigenvalues occurring in the space are. So, but you don't have any Galois theoretic interpretation or conjectural avatar or whatever of what the space actually is. Okay, and what I want to talk about is a conjecture that gives you this Zissleri space. Okay, and that's part B. By construction, this eigenvariety y, the eigenvariety is a Stein space. So in particular, well, I mean, maybe not in particular, but it by construction also comes with a coherent sheet whose global sections are more or less given by the space of p-adic automorphic forms. There exists a coherent sheaf M. I want to call this M dual for a reason which will maybe become clear later. There exists a coherent sheaf or M dual on Y such that the global sections of M dual are just, well, not quite the space of finite slope over convergent form, but it's topological dual. In some sense, it already explains why I want to kind of consider this M as a dual thing. So this really comes by the very construction. So the eigenvariety doesn't really know the space, but at least you can write down a coherent sheaf on it, which knows the space of p-adic automorphic forms. In the sense that it's a Stein space, this sheaf actually is unique once you've constructed it. Okay, so equivalently, and this is just a stupid reformulation. There exists, well, a priori, maybe only a complex of coherent sheaves, which I now really want to call M, which is a Grothendieck dual of this coherent sheaf M check, such that you can get rid of the dual here on the price of, well, replacing this by its Grothendieck dual and replacing cohomology by compactly supported cohomology. Okay, so R gamma C Y. Okay, so this is really compactly supported cohomology of coherent sheaves on a widget space, or on a Stein widget space, which is nothing to be afraid of. So kind of things like this were already in a very in a more classical way defined by Cariolotto, and at least for smooth spaces or complete intersections. And then there has been some work on this. Well, I mean, if we don't know anything about the singularities a priori, we maybe have to use some more heavy machinery to actually say what this is in the first place. But at least kind of at least due to Klaus and Scholz, there exists some robust framework where I can do things like this. Okay, and in some senses, the use of this here is artificial. Okay, I just want to get rid of this dual over here, and I think this coherent sheaf here is a more canonical object than this coherent sheaf. Okay. Yes.
Is it supposed to be the global setup?
What do you mean by independent of the global setup?
Choose some like unitary group or something, or
I think I don't understand the question. All this, of course, depends on the choice of the global setup. Like Y and M dual depend on kind of all the data that I chose.
maybe your subspace depends on less choice, no?
No, I think all these data here are precisely attached to kind of the group, the tame level, yeah, the group and the tame level. Or maybe I'm completely misunderstand the question. Maybe then later, in case I completely misunderstand.
Quick question.
Yes.
This why like you can attach a pseudo character or only like if there is discrete series, say.
No, over why you should kind of.
Not really this by Gauss representation, but like if you consider GL2 over imaginary quadratic field or GLN over Q, in general, you don't, unless I'm not aware.
Well, this is all kind of among the things where I said in the first place, don't be too critical for the.
No, that's how I read it, but I'm saying like, let's reformulate the question. Is it expected to be able to attach a pseudo character to such a way?
Yes. Yes. But I mean, like, let's say for the sake of this overview, I always want to be in the case where I can attach a pseudo character. The question basically is, I've given at least conjectural way to recover Y, the variety in terms of Galois representation. So the more or less obvious question, I guess, is can I give a purely Galois theoretic description of what the sheaf M is? Okay, so that's the first aim. So
That includes my question, right? I mean, you had to have a Galois representational line to be able to characterize.
well, I mean, like your question was already addressed when I said that Y is equal to something in terms of Galois representations. This means that for all points of Y, you must have a Galois representation, or at least a pseudo character. If I say conjecturally, this is the same. Okay, so let's say if Y has a conjectural description purely in terms of Galois representations, okay, so is there a conjectural description of my sheaf M purely in terms of Galois representations? And of course, the answer should be yes. Okay. Well, I mean, like maybe not of course, but the answer should be yes.
How canonical is this supposed to be? Do you just want to construct something by Galois theoretic methods that's isomorphic to M, or something with a preferred isomorphism to M?
A priori, maybe only kind of, well, a priori maybe only with an isomorphism which is equivariant for all the different structures that you have. So for hacker actions and so on and so on. I actually don't know how canonical this is or this can be. So there's the part C. As you know, by this recipe, how to describe maybe in Galois theoretic terms your space of finite slope spaces. Here, your space of finite slope overconvergent periodic automorphic forms. The question maybe also is, can you describe eigenspaces therein? Okay, so let's say given a point Y and my eigenvariety. So by definition, Y corresponds to two characters, one of the Hecke algebra away from P and one for the Atkin-Lena ring. These are the corresponding Hecke characters. And say L over QP is finite. Then, well, maybe for safety, I should assume that rho chi is a corresponding Galois representation. Is irreducible so that my formulation that I'm going to give in the second doesn't run into difficulties when I have to distinguish between a pseudo character or pseudo representation and a representation. Then I still have my coherent sheaves down here. Then the fiber of my coherent sheaf at this point is precisely dual to the corresponding eigensystem. Okay, it is dual to the eigenspace for the systems of eigenvalues, more or less by construction over here. And so if I first assume that y is a classical point, then this guy here contains a subspace of classical forms. Classical eigenspace. Which is non-zero. Which is some kind of tautology because I really just call this point classical if the subspace of classical forms in this one here is non-zero. Okay, so you have these 2 points. And now you can ask whether these are the same. Okay, so usually this inclusion star here star is an equality, which happens, for example, under small slope conditions. Then kind of eigensystems are automatically classical, which is basically kind of Kuhlmann's classicality criterion and generalizations thereof. That also work fine if your forms are what's called non-critical, etc. So there are conditions which guarantee this. So very often it's the case that you should expect that these spaces coincide.
Isn't that kind of the definition of non-critical?
I think my definition would involve the Galois representation, and then it would not be equivalent to this. But yeah. And for me, like in the crystalline case, for example, this would mean that you have a refinement which gives you a Frobenius stable flag in the Berlin representation, and you have the Hodge filtration. And non-criticality for me would mean that they are in general position. And this is this would imply equality, but it's not equivalent to equality. Certainly it is for GL2 also. Well, no, that's not true. But okay, whatever. Okay. So, but there are examples where this is not the case. Well, star is a proper inclusion. Okay, and there are maybe basically 2 cases that I know about. The first case, or the first maybe set of cases, were established by Judith Ludwig and Christian Johansson. which uses the group SL2, or forms of the group SL2. And then there are examples in the work of myself with Valentin Hernandez and Benjamin Schwan, where we consider definite unitary groups in 3 variables. Okay. And as I said, that there should be some Galois theoretic description of the sheaf M, or maybe of the sheaf M dual, that knows these eigenspaces. I'm in some sense here also asking for a Galois theoretic explanation of the fact that these spaces are not the same. Okay, so this is kind of, if this one here has an affirmative answer, then there must be some way to decide purely in terms of Galois representations whether these are the same or not. That's the aim in part C. The question is, can one decide in terms of Galois representations whether star is an equality? Okay, so these are so basically part B and part C are the things that I want to address in this talk. And maybe I will address part B in the modular curve case in order to kind of, first of all, lower the technical amount of detail that I have to talk about in order to state the conjecture, and certainly also in order to say that there was a proof, or at least some proof of a partial result.
It's for simplification that you take eigenspace and not generalized eigenspace.
You should be able to do the same with a generalized eigenspace once you know what the sheaf is, right? The sheaf also knows the generalized eigenspaces.
You expect your methods to be able to say something about the generalized eigenspace.
Well, in terms of a result, so for example, this result, that's really the eigenspace that we take in the end.
Can I ask a philosophical question?
These are the nicest questions because then the answer can be philosophical as well.
Why are you focusing particularly on the construction from overconvergent forms? I mean, the eigencurve also has an equally natural sheaf on it that's the sheaf of overconvergent modular symbols. And you could ask all of those questions about this sheaf as well, and the answers might be different.
Well, I didn't really say what forms is. And in the precise statement later on, I maybe rather take what you want with modular systems symbols. I mean, like what I take is kind of the Jaquet module of completed cohomology of modular curves. This is what I describe.
And in that case, I'll change my question back to the thing I thought you were saying.
The answer should be there should be. Yeah, the philosophical answer to the philosophical question is there should be a description, which is not the same one, but it still should be able to do this. One still should be able to do this, and I don't understand all the details of this, but there was some hints what one should do. Okay, but now let's leave the philosophical world, respectively the overview where everything is well, kind of very imprecise. So in order to formulate this in order to give the Galois theoretic, the conjectural Galois theoretic description of the sheaf M, I have to talk about stacks of analytic Feiger modules. And so this is a completely local thing. So let me write xn for the stack on which analytic spaces. Which maps spur A to pi gamma modules of rank n over the relative rubber wing for A. So just maybe some kind of appropriately completed tensor product of A with a rubber wing. Okay, and these are phi gamma modules, well, for the, say, single atomic tower over QP. So for simplicity, I will just stick to kind of fixing QP as my local field and not work with certain extensions. Okay, so you can write down this this group height, and we can prove it's a stack for kind of some Tate FPQC topology, and then you can do kind of fun things. So let B and GLM be the Borel. And I want to say XB is the stack of Feiger modules with B structure. With B structure, which means phi and gamma stable filtration. And by filtration, I really mean that the graded pieces are projective rank 1. Okay, and so these are the same thing, also known as triangular and Feiger modules. Well, that's really the definition for Feiger module to be triangular, that there exists a filtration like this. Maybe. Well, maybe this definition usually is just written down for a point. So as the A is just a point. But you just kind of consider the stack, and then maybe if T is a torus, which is inside here, then you also can write down XT, which is the stack of Feiger modules with T structure. And then as a torus is just a product of copies of GM, this turns out to be isomorphic to what I want to call T hat divided by T, where T hat is basically what was T hat before. So this is a space of continuous characters of T of QP, which is basically QP star to the n. So there's a nice analytic space on which the analytic group T, considered as a widget analytic group, acts trivially. Okay, just from the stack quotient for the trivial action, and that's what the stack is. Okay, and that's basically a result of Kidlaya, Potters, and Zhao, that the stack has this inscription. Okay. I've got a wee blackboard. So here's a theorem from my joint work with Valentin Hernandez and Benjamin Schra, which is not the work that I cited before, which is something which has to be written at some point. And I guess I'm the one to blame that this doesn't exist, but a survey of this can be found at least in the notes from the ERShares summer school 2 years ago. So the stacks XP and XT are rigid analytic Artin stacks. So if you kind of just transfer the definition of an Artin stack from the world of schemes to the world of rigid spaces, you rise with something like they must have representable diagonal, and then you must have a smooth cover by an actual rigid space. And at least for T, I already wrote down what the cover is. Okay, and for XB, you have to prove something. The fun part of the story is that the morphism, so you have a morphism from XB to the stack of all Fagger modules, which just forgets the filtration. And then you also have the map, the projection to XT, which using this isomorphism and the fact that the action here is trivial just gives you a map to T hat, to the space of characters of the torus. Okay, and this map, if you look into kind of the classical literature for kind of vector bundles on curves or something like this. So a Fagger module, basically, you should imagine as something closely related to an equivariant vector bundle on a curve, actually on the Fark-Fontaine curve. So it's like an equivariant vector bundle on a curve, and hence these moduli stacks draw a lot of intuition from the classical theory of vector bundles on algebraic curves. Okay, where you also can form this XB and so on and so on. And there it's known that this map XB to XN, or maybe this diagonal map, is rather nice. It's, for example, it's surjective, but it's not proper. Okay, and there exists a compactification of this map. I want to call this XB bar, and that's a Greenfeld compactification. Of this, which then is proper. I mean, it's a compactification. Of XB to XN times P-hat. Okay, so that's kind of, in some sense, very much inspired by the story for vector bundles on curves. Moreover, XB bar is rigid analytic Artin stack. So also this compactification is a nice guy in geometric terms. Sorry?
Does that imply that XN is an Artin stack?
No. First of all, this map has no reason to be smooth. Second of all, and this is kind of particular to the p-adic story, this map, or even the projection down to XN, has no reason to be, I mean, like has no reason, is not surjective. Like in the classical case, in the classical theory vector bundles on curves, this map is surjective. Okay, but in this kind of case of equivariant vector bundles, this actually fails, surjectivity fails. So you should rather imagine the image of the map to be Zariski dense in the infinite Pern sense. So the image of this map should be kind of the local analog of the infinite Pern. Okay, and so here are some local conjectures. So, these are things that one can prove, but here are a lot of things that I can't prove. So first of all, kind of the answer to your question whether this implies that xn actually is an Artin stack was no, but certainly I expect it to be an Artin stack for different reasons though. I just admit widget analytic. I mean, everything is widget analytic. Okay. Is an Artin stack of dimension equal to the dimension of the group I started with, which is GLN in my case, and it's normal and a local complete intersection. So this is a condition which certainly makes sense once you know that it's an Artin stack. The second thing is that XB is, well, you know it's an Artin stack, but it's of dimension equal to the dimension of B, which is kind of the thing I don't know how to prove. And I also want that it's normal at LCI. The third part then concerns the compactification XB bar is, well, I mean, if you compactify something of dimension B, you should expect that you don't change the dimension. So this certainly also should be dim B dimensional. I would hope that it's still normal, but it doesn't have any reason to be a local complete intersection. And that's actually something one can make precise, but it makes sense to expect that it's still Cohen-Macaulay. Okay. So, moreover, I expect that the projection of the compactified stack of B-Fagel modules to the stack of rank n-Fagel modules, maybe times this parameters, have a well-defined, let's say, scheme-theoretic image. Which I would call xn trianguline, which then is the original Artin stack. So if you can prove one, then this should be automatic given the properness of this map. But without being able to prove one, that's certainly a statement to be proved that you actually can make sense of this. So here you have trianguline locus in here. Let's call this G. And this map G now should be some kind of birational resolution, or at least partial resolution. So I expect this to be birational. Birational with geometrically connected fibers. And even kind of the nicest thing possible in this case would be that the derived push forward of the structure sheaf is a structure sheaf, right? That's an optimistic conjecture, so at least part 4. Okay, the other ones are, I think, rather safe. Part 4 maybe is a little bit optimistic. Yeah, but these are kind of really nice geometric objects, and they should satisfy really nice geometric properties. Okay, so let me maybe quickly give a few partial results. So, concerning the first part of the conjecture, there exists charts locally around widget analytic points. So if you fix the widget on the point of the stack xn, then it has a Zariski neighborhood, which is an Artin stack, which is smooth under an actual widget space. This doesn't imply the statement, basically for the usual reason in widget geometry, that a covering by open admissible subsets is not an admissible covering. Okay, so that's well, I mean, like, you maybe should work with adic spaces instead, and then you have more points where you just can produce coverings, but I can't so far produce these charts locally around points with large residue field. Okay, so that's kind of a statement or the state of the art here. The second part I want to say is that for 2 and 3, the dimension is okay. At least if n is less or equal to 4, and this automatically implies, well, using the actual construction of these stacks maybe, but it implies half of the statement on the singularities, namely here it implies LCI and here it implies convex. In order to prove it's normal, I would have to prove some stronger dimension bound than the dimension bounds that are necessary here. But I mean, like, I want to just tell you that in low dimension, you can kind of compute things and the statement is not out of the world. Okay, and part 4 is at least okay for n equal to 2. If n is equal to 2, then the whole of part 4 is okay. You can prove that there's a scheme-studic image which is an Artin stack, and that this map is a kind of rational resolution. Not a resolution because the kind of space is not smooth, but kind of has this property here. Okay, that's a geometric thing that you can prove in the local setup. And I should also remark that the story with the scheme-theoretic image is something that you somehow can, I'll not write it, but that you can prove at least after pullback to dynamic fibers of Galois deformation rings mapping to the space. And then you kind of get what we call the triangular variety in joint work with Benjamin and Christoph Preull. So after kind of resolving this issue that I don't know how to put it, it's an Artin stack, by pulling back to some actual nice space of Galois representations, you can certainly say something about the scheme-theoretic image. Okay, but I should move on because there are drinks awaiting us. I was told that I have no chance to go over time. The chairman of this afternoon session. Okay. So here are global results. So for the sake of time, I maybe will limit myself to just consider the case of the modular curves. So for GLQ. Okay, and then set in the paragraph my space of overconvergent finite slopes forms to be what David didn't expect. namely the Jacquet module. So this kind of the Hellmann and Jacquet module of the locally analytic vectors in completed cohomology of the tower of modular curves of k level kp. Okay, which you maybe also can rewrite as the cohomology at either Howey level of a certain explicit local kind of huge p-adic coefficient system on the modular curve at either Howey level. Okay, so that's my precise space of p-adic automorphic forms that I want to talk about. And then I want to have a more precise way to talk about a global stack of Galois representations. So this is really the stack. Stack is important here of odd two-dimensional continuous representations of Gal Q unramified at the good places of KP. Okay, but the stacking nature really is essential for a reason that I'm going to point out. Okay, so what kind of maps do you have? Well, you have this global guy, which maps via restriction of the Galois representation, the local Galois representation, to the stack of rank 2 Fager modules. Restrict plus apply the functor attaching a Fager module to a Galois representation, and then I maybe also take the product with the space of characters. And here, this guy receives the map from this compactification of the stack of B-Fager modules, which projects down to xt, which was p hat mod t. Okay, so you have a diagram like this, which allows you to formulate the following conjecture. So there exists Gal Q times Hecke equivariant isomorphism between your space of, maybe I rather should say, finite slope over convergent homology classes instead of forms, with the compactly supported cohomology on this stack x global times t hat of, and now I want to write down this explicit sheaf that I was looking for in the introductory part. Okay, and what is this? This is the pullback of the push forward of an explicit sheaf, which is kind of the structure sheaf on xd bar, and then twisted by an algebraic character. So this is kind of the twist by an algebraic character of t, which I can perform just because this projects down to the classifying space of T. Okay, so this I can further project down to point modulo T, and kind of characters of T give you coherent sheaves or kind of line bundles on point mod T. So you can pull it back, and this way make sense of this twist, which actually is important. And this V here is the universal family of Gal Q representations on the global stack of Gal representations. Okay, so that's the precise form of the conjecture, up to the fact that I'm, as I said in the introduction, ignoring places away from P, bad places away from P. Okay, they also should kind of contribute somewhere here, if KP is not hyper special, but I'm in some sense just too lazy to write this down. Okay, and I will finish with the theorem of myself with Shijiang Wu, saying that the conjecture is true after localizing at non-Eisenstein ideals. Okay. I will finish after one remark. I said that the stacky nature of this guy here is important. Okay, and equally important is this twist over here. Okay, and why this? I mean, even at irreducible Galois representations, there is some kind of leftover residual action of the stabilizer, which maybe is just the center or something like this. But there is some kind of inertial group action. Okay, and if you don't take this inertial group action into account, then kind of the cohomology here would be too large. Okay, it would have kind of other eigenspaces. And well, this family of Galois representation here does not have the trivial inertial action on the stack, but rather kind of comes by pullback from kind of the universal or the standard GL2 representation on point mod GL2. Okay, so it has some weights. Okay, and this weights kind of automatically give you kind of a non-trivial inertial action, which is kind of really non-trivial. So you wouldn't expect any global section unless you compensate this by some other means. Okay, and this character here precisely compensates this. So that's kind of, there are some nasty details in there, but kind of in the end, this clean formula takes care about everything. Okay, and here I stop.
Can you compare any